What is quantum mechanics? Quantum mechanics attempts to explain the behavior of subatomic particles at the nanoscopic level. It is one of the most successful branches of physics, and there are countless examples of scientific experiments confirming predictions made by the laws of quantum mechanics. What is a particle? One of the particles you will be most familiar with will be the electron. These orbit the nucleus of atoms, and the nucleus is made up of two other particles, protons and neutrons. The electron is an elementary particle, one of the fundamental constituents of the universe. Scientists have found that protons and neutrons are made up of other particles called quarks. Quarks are also elementary particles. Quarks are held together by gluons. Gluons are also particles, but they are different from the quarks. They are the particles that produce the strong force that holds the quarks together. Gluons are also behind the strong force which holds the protons and neutrons together within the nuclei of the atom. Gluons do this by mediating the strong force between the quarks or between the protons and the neutrons, as the case may be. The types of particles like electrons and quarks we can think of as creating matter, and the types of particles like gluons we can think of as creating the forces. There are four forces that we know of: the strong force, the electromagnetic force, the weak force, and gravity. The Standard Model of Elementary Particles. The Standard Model of Elementary Particles describes how all the elementary particles and forces in the universe behave apart from gravity. How gravity works in the quantum realm is actually not very well understood. We have the matter particles, or fermions, which are divided into quarks and leptons. There are 6 quarks, up, down, charm, strange, top and bottom. There are 6 leptons, electron, muon, tau, electron neutrino, muon neutrino, and tau neutrino. We then have the force carrier particles, otherwise known as gauge bosons. The gluons we have discussed already. The photons are particles of light and carry the electromagnetic force, which holds the electrons in atoms. The W and Z bosons carry the weak nuclear force, which is involved in some forms of radioactivity and plays a role in how the sun burns. Owing to the discovery of the Higgs boson in 2012, that particular particle has achieved something of a celebrity status. Countless Higgs bosons make up the Higgs field, and it is the interaction with this field that gives other particles their mass. For example, the top quark is interacting with the Higgs field, and this is what is giving the top quark its mass. And the final boson we turn our attention to is the graviton, which is a hypothetical particle that mediates the gravitational force. Quantum leap. In the early 19th century, it was theorized that at the subatomic level, energy can only be released and absorbed in discrete indivisible units called quanta. This means electrons have fixed orbits around the nucleus of the atom as their energy comes in discrete amounts. When the electron gets excited or de-excited, they will absorb or emit a specific quanta of energy, which will mean they leap from one orbit to another without inhabiting the space in between. This is called the quantum leap. In essence, there are places within the atom that the electron will be likely to be, and other places where they won't, as energy is being absorbed and released in discrete units. Particles behave like waves. There's a famous experiment in quantum physics called the double-slit experiment, which exposed something about particles that still surprises us today. Particles display both particle-like and wave-like behavior. In a version of the experiment, on a larger scale, we have a gun that shoots tennis balls one by one at a detector, which will register where the tennis balls land. In between the gun and detector, we place a barrier with 2 slits, which will leave openings for any tennis balls to go through. Over a period of time, and after many tennis balls, a pattern emerges on the detector, indicating where the tennis balls have landed. The results show that the balls which have not been blocked have landed directly behind the slits in the barrier. If we replicate this experiment, but on the subatomic scale, and use electrons instead of tennis balls, we expect similar results. But this was not the case. Scientists found that when the gun shoots electrons one by one toward the detector and past the double-slit barrier, the pattern that emerged on the detector looked like this. The electrons landed not just behind the 2 slits, but in narrow strips across the length of the detector, and a significant number of electrons even landed straight behind the middle of the barrier. The pattern that emerged is an interference pattern and is associated with the behavior of waves. Imagine we have two waves that interact. The peak of the waves will combine to form a higher peak, and the troughs will combine to create a deeper trough. And when a peak and trough meet, they will cancel each other out. So if we imagine that our electrons are less tennis ball-like and more wave-like, then what happens? This is a wave from above. The black lines represent a peak, and the spaces in between are the troughs. When an electron goes through the double slit, its wave is split in two, and these waves then interact. The peaks meet here and reinforce each other, creating higher peaks, and the troughs meet here, also reinforcing each other, creating deeper troughs. And here a peak and a trough meet, cancelling each other out. The interaction between the waves results in the interference pattern at the detector screen. Where the waves are most intense, we find more of the electrons on the detector screen, and where they cancel each other out, there are no electrons on the detector screen. Erwin Schrödinger came up with an equation for the electron's wave function, and using this equation, we can find out the probability of the electron being in a particular location. Think of the wave as a bundle of probabilities, and the size of the wave in any location predicts the likelihood that the electron will be found there if it is looked for. That is why on the detector screen we observe most of the electrons landing in the places where the electron's wave is at its most intense. It seems as if the electron is not in a fixed position but has different probabilities of being in many different places at once. The act of measurement. To observe the electron's wave function going through both slits at the same time, detectors were placed next to the slits to capture this activity. But when this was done, something strange happened. The electron stopped behaving like waves and went through one or other of the slits and landed on the detector screen to form the two-striped pattern rather than the interference pattern. It seemed as if the act of measuring did something to collapse the wave function. The superposition principle. The superposition principle states that while we do not measure the electron for its position, it is in all the possible positions it could be in at the same time, and when we observe it, the superposition collapses. So in this illustration, when our detector is off, our electron is in all of the possible positions or states it could be in simultaneously. But when we switch our detector on, the superposition collapses and the electron gives up all of its possible states to choose just the one. That is why we were not able to observe the electron's wave function going through the double slits. The very act of attempting to observe made the electron's wave function collapse. The electron gave up its superposition and chose just the one state to be in. I.e., the electrons actually reverted to particle-like behavior, and that is why instead of going through both of the slits, the electrons that landed on the back detector chose to go through either one or the other of the slits. Let's use one of the most famous thought experiments to further illustrate what quantum mechanics is saying about the electron and the superposition. We turn our attention to Schrödinger's cat. Schrödinger's cat. Erwin Schrödinger described a thought experiment where a cat was placed in a covered box with a radioactive sample that has a 50% chance of decaying and killing the cat. While the box is covered, we have no idea if the cat is dead or alive, and only once we open the box will we know if the cat made it or not. So if the cat were similar to an electron using the superposition principle, we would say that while the box was covered and the cat was not being observed, the cat was both alive and dead at the same time, in order for it to be in all the states it could possibly be in. Only when we lifted the cover to observe the cat did its superposition collapse for it to be either alive or dead. Obviously this feels intuitively wrong, and the reason why this thought experiment was employed was to illustrate how odd the laws of quantum mechanics are when it comes to describing the behavior of particles.
Since the 1960s, the power of our brain machines has kept growing exponentially, allowing computers to get smaller and more powerful at the same time. But this process is about to meet its physical limits. Computer parts are approaching the size of an atom. To understand why this is a problem, we have to clear up some basics. A computer is made up of very simple components doing very simple things, representing data, the means of processing it, and control mechanisms. Computer chips contain modules, which contain logic gates, which contain transistors. This information is made up of bits which can be set to either 0 or 1. Combinations of several bits are used to represent more complex information. Transistors are combined to create logic gates which still do very simple stuff. Combinations of logic gates finally form meaningful modules, say for adding two numbers. Once you can add, you can also multiply, and once you can multiply, you can basically do anything. Since all basic operations are literally simpler than first-grade math, you can imagine a computer as a group of 7-year-olds answering really basic math questions. A large enough bunch of them could compute anything from astrophysics to Zelda. However, with parts getting tinier and tinier, quantum physics are making things tricky. In a nutshell, a transistor is just an electric switch. Electricity is electrons moving from one place to another, so a switch is a passage that can block electrons from moving in one direction. Today, a typical scale for transistors is 14 nanometers, which is about 8 times less than the HIV virus's diameter and 500 times smaller than a red blood cell's. As transistors are shrinking to the size of only a few atoms, electrons may just transfer themselves to the other side of a blocked passage via a process called quantum tunneling. In the quantum realm, physics works quite differently from the predictable ways we're used to, and traditional computers just stop making sense. We are approaching a real physical barrier for our technological progress. To solve this problem, scientists are trying to use these unusual quantum properties to their advantage by building quantum computers. In normal computers, bits are the smallest units of information. Quantum computers use qubits, which can also be set to one of two values. A qubit can be any two-level quantum system, such as a spin in a magnetic field or a single photon. 0 and 1 are this system's possible states, like the photon's horizontal or vertical polarization. In the quantum world, the qubit doesn't have to be in just one of those, it can be in any proportions of both states at once. This is called superposition. But as soon as you test its value, say by sending the photon through a filter, it has to decide to be either vertically or horizontally polarized. So as long as it's unobserved, the qubit is in a superposition of probabilities for 0 and 1, and you can't predict which it will be. But the instant you measure it, it collapses into one of the definite states. Superposition is a game changer. 4 classical bits can be in one of 2 to the power of 4 different configurations at a time. That's 16 possible combinations, out of which you can use just one. 4 qubits in superposition, however, can be in all of those 16 combinations at once. This number grows exponentially with each extra qubit. 20 of them can already store 1,000,000 values in parallel. A really weird and unintuitive property qubits can have is entanglement, a close connection that makes each of the qubits react to a change in the other's state instantaneously, no matter how far they are apart. This means that when measuring just one entangled qubit, you can directly deduce properties of its partners without having to look. Qubit manipulation is a mind-bender as well. A normal logic gate gets a simple set of inputs and produces one definite output. A quantum gate manipulates an input of superpositions, rotates probabilities, and produces another superposition as its output. So a quantum computer sets up some qubits, applies quantum gates to entangle them and manipulate probabilities, and finally measures the outcome, collapsing superpositions to an actual sequence of zeros and ones. What this means is that you get the entire lot of calculations that are possible with your setup all done at the same time. Ultimately, you can only measure one of the results, and it will only probably be the one you want, so you may have to double-check and try again. But by cleverly exploiting superposition and entanglement, this can be exponentially more efficient than would ever be possible on a normal computer. So while quantum computers will probably not replace our home computers, in some areas they are vastly superior. One of them is database searching. To find something in a database, a normal computer may have to test every single one of its entries. Quantum algorithms need only the square root of that time, which for large databases is a huge difference. Another really exciting new use is simulations. Simulations of the quantum world are very intense on resources, and even for bigger structures such as molecules, they often lack accuracy. So why not simulate quantum physics with actual quantum physics? Quantum simulations could provide new insights on proteins that might revolutionize medicine. Right now, we don't know if quantum computers will be just a very specialized tool or a big revolution for humanity.